Hello everyone. I am Radhika and this is my very first video on the tree series. So from the very first problem which we will solve is the binary tree pre-order traversal. Prerequisite is that you should have a strong grasp of recursion and the iterative process. For the pre-order traversal, we'll be using two methods. The first one is the recursion method and the second one will be the iterative method. First, we'll solve this problem through recursion. Okay. Uh, Now in this question, we are always given the root of the tree. So here the root given as 1. Now we need to give the pre-order solution of this tree. That is what, and we need to store it in a vector. So for the first thing, we should know that if we are doing a pre-order traversal, we store first the root element, then the left child, and then the right child. Fine. So for this example one, we are given the root 1. So if I create a vector, so first I'll store the root element, then I'll go to the left child. And you should know that in recursion, if we are going to the left, then we should traverse till the extreme left at a point till the point where we can't encounter any further left node. And as soon as we find null value, we return back and we go to the right child and then again go to the extreme left. Fine. So after storing 1 in the vector, we move to the left, but there's no left node present. We return, come back, and then we move to the right child. We store the right value as 2, and then uh, taking now I'll take 2 as the root node of this right subtree. Fine. So for that node 2, we have a left subtree and a right subtree. So as I told you that if we move to the right child, we'll go to the extreme left, and if we didn't find any node, we'll come back and we go to the right. Now after 2, we go to the left child, which is 3. So we store 3. Now taking 3 as the root node, we go to the left, but there's no value present. We come back. We go to the right. There's no right node present. We come back, and we have completed the traversal for 3. We return back to 2. Now I move to the right side, right child, right subtree, but we find that there's no right subtree present. We return back from 2 and then to 1, and then the traversal is over. So we can say the pre-order traversal is 1 to 3, which is the expected traversal. Fine. Taking example number 2, and then we'll approach the coding part. We are given the root node as 1. Fine. Then we need to move to the left child of 1 of the root node. So first we store the root node, then we move to the left child, which is 2. Then taking 2 as the left child, we again move to the left. We find 4. So as I said, told you that we move to the extreme left. Now after 4, there's no left node present. So we check the right child of 4. There's also not a right child present. We return back to 2. Now, checking the right child or the right subtree of 2, we find 5. So we store 5. Now, going to its left child, we find 6. So we store 6 in our vector. Now, there's no left or right child present for the 6. We return back to 5. We go to the right child, which is 7. And similarly, we can say that there's no left and right child present. We return back to 5. Fine. Then we say that the traversal for 5 is complete. We return back to 2. Same for 2. We return back to 1. And now we go to the right child or the right subtree of 1. So now moving to the right subtree, we encounter 3. So we can say 3 is the root node of this subtree. We go to its left, no node present. We come back, we move to the right. We find 8 is there. So we store 8. Now for 8, we go to the left, which is 9. No further left node present. We return back. No right node is also not present. So both left and right child are empty, null. We return back to 8. We go to the right child. There's no right child present. We return back. We then return to 3 itself and then to 1. So we can say that our whole pre-order traversal has been completed, and the vector contains the pre-order traversal of this tree. So it's 1, 2, 4, 5, 6, 7, 3, 8, 9. That's the correct answer. Now, I suppose that you have understood the concept of pre-order traversal. Now it's time to code. Fine. So we know that we need a vector to store our answer. So I define a vector to store our preorder traversal, and we call a preorder function which returns us the output with preorder, and then this I pass the root node and my answer vector, and when it's get completed I return the vector. Now I need to define the function. So void preorder pre node star root vector int and answer. Fine. Now we got a root node and the answer. Now we know that as soon as we get the root node, we need to store it in our vector. So first I store the root node in the vector answer dot pushback root node. Now after storing the root node, we move to the left child. So I say I'll call this function again and I'll pass the left child of the root as the new root of the left subtree. Are you getting it? I pass the left child of the root node as the root node of the next left subtree. Fine. And I again pass the answer vector. This is for storing left child. Okay. Now we move to the right child. Right child. Fine. Now again call the function and its root right and then give answer. Now this is how we'll be storing all the nodes values in our vector. But there's one thing missing. We are using the recursion approach, and we need to know that we have a base case condition to end our recursion. So I already told you that if we found that there's no new node present, we return back. So if I say that if my root node is null, I return root equals to null, I return back, and then I'll simply return the answer vector. Fine. Now just compile it. Okay, there's some issue. We need to store the actual value, the root. Yeah. So let's submit it. Fine. We have to traverse till the as the height of the tree. Okay, so if I'm at 1, then I'll go to 2, then I go to 4. So if suppose we can say that we are traversing the height of the tree. Fine. So we can say O of h, and we know that the height is O of log n. Fine. Now talking about that if it is a skew tree, if I show you what is a skew tree, it's images. So this is our skew tree. Fine. If we go to the extreme left, if all the elements are left side or on the right side, so if we are traversing this kind of tree, then we need to traverse all the elements of the tree to get to the last node. So I can say that in this case, the time complexity will go up to, in the worst case, it can go to O of n. So we can say that the time complexity in the worst case can go to O of n. But if I talk about the space complexity, since we are using a recursion, we are storing a recursion stack space. So the stack space will be taking a space of O of n. So the space complexity will be O of n, and we are just ignoring the vector answer, and because it's already defined that we need to return a vector. But if I take it back, if I also consider that, so I require equivalent to O of 2n space to store this. Okay, so this is the solution for the recursion part. Now, in the next part, I'll be covering the iterative approach. So yeah, this is the second part of the pre-order traversal question. We'll be using the iterative approach to solve this question. So for using the iterative approach, we'll be requiring a stack data structure. Fine. And in the stack data structure, we'll be storing the elements like first the root element, then its right child, and then its left child. Fine. I'm storing in this manner because when I pop the elements from the stack, pop the elements, Then I get first the I'll first get the left child and then the right child. Fine. So this is how, and this is the expected way to store any element in a pre-order manner. So if we try run this for the first example, okay, so we are given a stack, and initially we store an element in a stack. We can say we store one. Now to traverse its neighboring nodes or its child, we first need to pop one from the stack and need to store it in a vector, which is our answer vector. So we define a vector, and I store one in it, and I pop one from the stack. Now since I popped it, I need to traverse its left child and right child. So as I told you, we need to first go to right child. So I'm going to 2 now, and I store it in the stack. Okay, now I'm at 2. Now I will store the left child also of that, so of the node, of the current node, of the current root node. So the current root node left child, there's no one. So we come back. Now we'll see who's the topmost element of the stack. We encounter 2. So we'll pop 2 from the stack and we'll put it in a vector, and in the stack we'll put the right and the left child of the node 2. So there's no right child present, no need to push anything in the stack. If there's a left child, yes, so we put 3 into the stack. Now assuming now who's the topmost element in the stack, which is 3, so we move to it. So we pop 3 from the stack and push it in a vector, and in the stack we'll be pushing its right child and the left child, but since there are no child present, we'll return back, and we see that there is no element in the stack, means a stack is empty. So as soon as a stack gets empty, we'll return this answer vector. It means that we have traversed all the elements of the tree. So this is the approach we'll be using to solve this question. Fine. uh, if I do the same approach, follow the same approach for the second question, uh, we have this vector to store our output and a stack to store its child nodes. Fine. So first we initially push root node in the stack. Now we pop root node from the stack and put it in a vector. Fine, the output vector. And in the stack, we'll be storing the right child and the left child. So first we store the right child and then the left child. Now you see that the topmost element of the stack is 2. So I pop 2 from the stack and I put it in the vector. Now, as I told you, we'll go to the right child and the left child of 2. So I encountered the right child to be 5. So I put 5 into the stack, and then I'll put 4 into the stack. Now you can see the topmost element is now 4. So I remove 4 from the stack and I put it in the vector. Now, as I put it in the vector, I say that who are the right and left child, but there's no one. So no need to insert anything in the stack, and we come back. Fine. Now, who is the topmost element of the stack? So we encountered 5. We'll pop 5 from the stack and put it in the vector. Now we'll see who's the right and the left child. We say that 7 and 6. So we insert first 7, which is the right child, and 6, which is the left child. Now we again see who is on the top of the stack. We encountered 6. We pop 6 from the stack and we put it in the vector. Fine. Now we say who's the right and the left child of 6. There's no one present. Come back. Fine. Now we come to 7. 7 is the topmost element of the stack. So we pop it out, we'll store it in our vector. Now we say that who's the right child and the left child, there's no one. We come back, we have completed the pre-order traversal for 5 as a root node of the right subtree. We come back to 2, we have completed for 2. So we can say now that who is the now the topmost element of the stack is 3. So we see who is the right child. We encountered 8. So first we'll pop 3 from the stack and we'll put it over here, and we'll put 8 into the stack. Now there's no right node present. We don't put anything into the stack. Now I'll assume that who's the top of the stack? 8. So I pop 8 from the stack. I put it into the vector and see who is the right child present. There's no one. It's okay. Who's the left child? 9. I put it into the stack. Now we pop 9 from the stack, put it in the vector, and we see who is the left and the right child of 9. There's no one. So we can say that our stack is empty, and since our stack is empty right now, we can say that we have traversed the entire tree. So this vector will contain the pre-order traversal of this tree. Fine. So this is how we will solve the questions through iterative approach. So let's get to the coding part. So now it's time to code the solution. So First thing we need to remember is if we need to define a vector to store our answer. Uh, Fine. Now, the base condition, if we assume that if our root, edge case, if our root is null, we return this empty vector. Fine. But if it's not, we define a stack to store our nodes. Fine. So it's over here. And initially we push the root element. So I pushed root in the stack. Now we'll apply a condition on the stack that till the point our stack is not empty, we'll keep on traversing the tree. Okay. Stack dot empty. It's not empty. This condition will remain true. And we say that when we see that first we need to get the first element from the stack, the topmost element. So I store it in a new node and I get the stack topmost element. And we know that we need to pop that element also. So we pop it out. Now we have got the topmost element. We'll store it in the vector. Fine. And we need to store its value. Fine. Now, as soon as we have stored it in the vector, we'll see who is the right and the left child. If I say if store right child, if we say that if we have a root right child, if it's not null, okay, if root is not null, right child not null, we store the right child in the stack, to stack dot push root right. Fine. And similarly for the right left child, if we root we have left child, we'll push that into the stack. Fine. So this is how we'll proceed with the iterative approach, and at the end when our stack will become empty, we'll return this vector. Fine. So let's compile this. Okay, there's some issue. So now the issue is resolved. We need to push the same element. We were by mistakenly pushing root right element, which is wrong. So now we have passed all the test cases. Now talking about the time complexity and the space complexity. So we know that if we talk about the time complexity of this problem, we can say that to push or pop any element in a stack, we require O of one time. Okay, that much constant amount of time we require, but we are doing it for all the elements of the tree. So if we say that for one element we are requiring O of one time, so for n elements we require O of n time. So that much will be the time complexity. And we talk about the space complexity. So we are storing elements up to in a stack up to the height of the tree. So the time complexity will be the height of the tree, means the maximum amount of elements which you can store in a stack will be up to the height of the tree. So that's the space complexity. So that's all for this question. In the next question, we'll be covering the in order traversal of the binary tree. Thank you.